Hey everybody. I'm going to pick up with another idea from still talking about functions of several variables, in particular functions of two variables. So I want to start with a pretty simple example of one. Suppose I was producing, let's say, some kind of containers, and the containers were to have a square base, right, and then up some height, right? So they had to have a square base and then they could go up to some height, right? So let's just call the side of the square base S and the height H. Then the volume of this container is a function of, sorry, I'm going to change this to L instead of H, I think, just to avoid some confusion in a moment. In either way, this just calling that the length instead of the height. So in either case, this volume is the function of two variables, right? We would take the length and multiply it by the side squared, okay? So what I have over here on the left is a table showing various values of the side and the length and the volumes you would get from that, right? So if you look down this left column, this is the side lengths, and I just did 1 through 9, and then the top row is the lengths, you know, the height length, 1 through 9 as well. So if you pick some particular square, right? So this square here that I've highlighted is if you make a side, the square base side 2 and the height 2, then you'll have 2 squared times 2 is 8, right? Now here you have a height of 8 and the side length of 4, so 16 times 8 gives us this 128, and so forth, right? So here's all of our different volumes for these particular values. What I want to notice in this, right? Let's think about change, right? We've a lot of first quarter calculus. And then throughout, you revisit this idea of a rate of change. How does one thing change as you change a different thing, right? So you usually take the input of your function and say, if I change the input of the function, what happens to the output of the function? That's what our derivative tells us. But now we have two inputs, right? And we can still talk about this, but we have to be a little bit more careful. For instance, notice here, if I'm in this square, for where both the side and the heights are 2, where we'd have a cube, that would give us a cube of volume 8. If I make my side a little bit bigger by 1 unit, right, that would be moving down this chart, I end up with a, oh, sorry, I'm looking at the wrong numbers. That would be side length 3, so get 3 squared times 2 gives me 18. On the other hand, if I change the height by 1 unit, I still increase the volume, but not by as much, right? Notice there's a big difference in how each variable here affects it. Pick another square. For instance, I'll pick this square down here, 216. If I change the side length to the base by 1, right, we go up by, what, 78 units? Whereas if I change the height by 1, I'm only going up by 36 units. And so in all these cases, a change in the base is much stronger, has a much stronger effect on the change in the volume, right? And so we're getting, so we have this idea of a rate of change. How does the volume change, the input change? But it depends on which input we're looking at, okay? And we can see this here, right? It makes sense the side length changes this more because it gets squared. So a little change when you change a number. So for instance, if you change 9 to a 10, you change the square of that from 81 to 100, right? That unit change turns into a much larger change once you square it. So we want to kind of investigate this idea. So I'm going to do something first. I'm going to look at, I'm going to define a new function. I'm going to call it A of L, okay? And let me actually clean this up a little bit. We're going to look at one particular portion of this screen. Suppose let's look at this portion where our height is 5 and our side length is 4. So I've highlighted that square, right? 4 squared gives me 16 times 5 gives me 80. So I'm highlighting that square. So what I'm going to define is a function a of L. What this function is tells me what the volume of our box is if I only consider the L variable changing, right? The length of this box. Okay, so the way I've written it is A of L is just V of L comma 4, meaning if you take V, the function of volumes, and fix S to be 4, we're only now considering these boxes that have a base side length of 4. We get the function that's pretty simple. I'm just putting in 4 for S, and I get L times 16. Right? And I can ask the question, what happens to A, which remember is still the volume of the box. It's just I've turned this into a function of one variable by fixing one of them. A prime of L, well, I can just use my regular derivative rules. You've got the variable times a constant. All you have is the constant. Okay. And for instance, let's look over here at our values. If you look at the values on either side of L equals 5, right? So if you think about an incremental change in L, for instance, if I look at L of 5 minus L of 4 over the change in L, over the change, not L of 4, this should be A of 4, excuse me. A of 5 minus A of 4, pardon me, over the change in L. So I'm just looking at what happens when I change my side length from 4 to 5. So the change in L is 1, A5 is 80, minus 64 is equal to 16. Let's look at what happens after a side length of 5. If we increase it, look at the change from A6 to A5. In other words, the change in volume, if I change that height by 1 unit, and I've got 96 minus 80, again, is 16, right? Remember, delta L here is just 1. I'm looking at unit incremental changes in L. Well, this makes sense because look at A of L, it's a linear function in L, right? Remember, we fixed S, so we just get a 16 where the S square was. And so that's maybe one way to define a linear function, a function whose rate of change is constant, and that's what we're seeing. It doesn't matter, it's precisely 16 at all these values. Now let's compare to a different function. Let's take B of S. This is going to be the volume if we fix the height at 5 and leave S to vary, and I get the function 5s squared. Okay, so it's kind of a novel concept, just like over here. We're fixing one of the variables in our original function. What that creates is a function of one variable because one of the variables can't vary anymore, right? So I've got this B of S. B prime of S, how does the volume change as I change the side length of the base, is 10s. And if I look at this point that we're looking at 4, this will be 10 times 4, or 40, right? Let's play the same game. So before, when I was changing L, that was moving horizontally across this table. Changing S is moving vertically. So I want to look at the change between one smaller side length to the one we just investigated. In other words, B of 5 minus B of 4 over delta S, which again is just 1. So B of 5 minus, I wanted this to be, well, it doesn't matter. Yeah, let's do it the way I intended. So first I'm looking between B of 4 and B of 3, right? So we were looking at the point where our side length was 4. I want to look what happened before we got there and what happens after we get there, the change right before and the change right after. So B of 4 is 80, B of 3 is 45, we get 35. Meanwhile, b of 5 minus b of 4. What is the change, the average rate over change in the unit interval after the place we just measured by the derivative? Well, b of 5 is 125 minus 80 over 1 gives me 45. Notice our derivative is right in between these two, right? The rate of change with respect to changing the side length is a little slower before we get to this point and a little after, and at that point it's right in between those two, right? So the bigger our radius gets, the more changing it starts to affect it, is what we're seeing. Not our radius, our side length, okay? So what did we look at? We took a look at this table to investigate how this function of several variables, of two variables, changes depending on which variable we changed, right? And two big takeaways. It's not the same for each variable, right? It's not the same for each variable. And the way we can look at how it changes for each variable is fixing the other one. I want to know how the height changed the volume. Well, I keep the side length constant, and vice versa over here. Keep the height constant and change the side length and see what happens to the volume. So this is the idea we're going to use to define variables for these functions. Define derivatives for these functions of several variables. Okay. So let me write down how this is going to look. Let's get a new page. Let's clear all of this. All right, so we're going to say, I'm going to start with a function, f of x, y, right? It's some function of several variables, or in this case, two variables. We'll define, let's say, given f of x, y, and ab is a point in the domain for which the following exist. And I'll say more about that when we get there, okay? So what we're going to do is we're going to start by, I'm going to define a new function called g of x equals f of x comma b. Just like before, we have fixed the y variable, and we're going to look at what happens when the x variable changes, right? We're going to give this a notation. We're going to give it a few notations. Here's one notation. I'm putting a little f with a little subscript x, and we're taking its derivative at this point, ab, right? So this is a subscript saying I'm taking the derivative in the x direction, or in other words, I'm seeing how f changes as s changes as f. I'm seeing how f changes as x changes by fixing y. And the way we're going to do it is just using this function g, because g, just like in those previous examples, is just a function of a single variable. You fix b as a constant, g is just a function of a single variable, so we just define this to be the derivative of g at a. Well, exactly what is that? That's going to be the limit as h goes to 0 of g of a plus h minus g of a over h. Should recognize this as the derivative of g, our definition of the derivative at a point. But what is g of a? G of a by definition, g of a by definition is defined in terms of f. This is f of a plus h comma b minus f of a over h. And this is what we'll call the partial derivative of f with respect to x. We're measuring how f changes as x changes. In this case, we're looking at a particular point, at the point ab, okay? This is what I meant by when the following exists. Of course, this limit has to exist, just like in the old derivatives, the single variable derivatives. sometimes these limits don't exist and we don't have a derivative. But in the case that they exist, this is how we find it. We do a similar thing in the y direction, except in this case, we're fixing the x variable and we're adding a little bit to the y variable and seeing how things change in this case. So these are our two partial derivatives. Okay. These are this is the partial derivative of f with respect to x, the partial derivative of f with respect to y. Okay. Further, let's push this one further. We can generalize this. Instead of looking at a particular point, we can come up with the derivative as a function. And so let's say the partial derivatives of f of x, y with respect to x and y are f of x, the partial with respect to x of f with the partial of f with respect to x is going to be the limit as h goes to 0 of f of x plus h minus, oops, sorry, I forgot the second half of this, f of x plus h comma y minus f of xy over h. It's exactly the same as what we did in here, except we're not fixing a particular point. We're thinking about doing this at any given pair of points, any given coordinate point. And then in the y direction, we do a similar thing. The limit as h goes to 0 of f of x comma y plus h minus f of x y all over h. Okay. So that's the formula. Now, it might look ugly, but it turns out this is going to be pretty straightforward to deal with. Okay. In fact, let's do a couple of examples and then we'll look at some geometric interpretations of this. Because in order to do this, we just regard, well, let's just do an example. This will be the easiest way to explain this, I think. Let's look at the function f of xy is equal to x squared y minus y. I'm going to start by computing the partial with respect to x. The idea is I consider y as a constant and x as my variable. So if I take a derivative, like let's do a little side example over here. Let's say I had a function f of x, single variable function of x squared times 3 minus 1. What happens to these constants? Well, this constant being multiplied by the function stays. I get 2x times 3 or 6x, and this constant disappears. The exact same thing happens over here. The 2 comes down, the exponent gets lowered by 1, our regular derivative rule, but I'm thinking of y as a constant, and so it stays, just like the constant 3 stayed here, right? I multiplied it by the 2 from the exponent, but that constant goes with it. However, a constant add or subtracted disappears, right? And so there's our partial derivative with respect to x. Our partial derivative with respect to y, I've got y, again, I'm thinking of x squared as a constant now, because now I'm thinking about the y derivative. If you have a constant times y and you take the derivative, you get the constant, and then the minus y has a derivative of minus 1. So all of our regular derivative rules still apply. The big challenge is training your eye to look at an X or a Y and keep one of them as a constant and one of them as the variable, right? So the one that you're taking the derivative with respect to is the one that's the variable, and the other one is the constant. Let's do a couple more examples. Let's see, how about, let's do a couple slightly harder ones. F of xy equals sine of xy. If I take the derivative with respect to y, sorry, with respect to x, so we've got a chain rule here because we've got a function inside and we've got a function outside. So the derivative of sine is cosine of xy. I'm thinking of x as my variable, which means I'm thinking of y as a constant. If I took the derivative of the sine of 2x, what do I end up with? Cosine of 2x, but then I have to use the chain rule and I multiply by the constant that's multiplying x. I have to multiply by the derivative of the inside. The derivative of a constant times x is just that constant. Well, now the constant, I'm thinking of y as a constant, that comes out is y. When I take f of y, sorry, the derivative with respect to y, I get the same thing, only now x is playing the role of the constant and gets multiplied because of the chain rule. Okay, so I switched which one I'm thinking of as the constant in each case, right? But this thing out front, that's a variable, shows up because I'm treating it like a constant. Just like the 2 comes out from the chain rule here, the y comes out from the chain rule here, and the x comes out from the chain rule here. Those are the constants attached to our variables. All right, let's do one more. Let's do f of xy is equal to, how about x over y? So now, maybe to make this look a little bit easier to deal with, this is 1 over y times x. If I'm taking the derivative with respect to x, 1 over y is a constant, 1 over y is a constant, and we're multiplying a constant times a variable, the derivative is just the constant. Meanwhile, f of y, I'm looking at the exact same formula, but now x is the constant, and 1 over y is the variable. The derivative of 1 over y is negative 1 over y squared, but we multiply by the constant x goes along for the ride, right? So two very different derivatives from this rule, depending on which direction we are looking at. Okay, so let's take a look at some graphs to maybe get a better understanding of what these things mean. So first, let's just handle one pretty intuitively, and then we'll go into a little more detail with the second one. Let me clear, sorry, I'll clear all this. And I want to look at, let's look at this one first. Here's an interesting surface. We often call this a saddle point, right? So for instance, if we look, the red axis is the x-axis and the green axis is the y-axis. Let's imagine, I'll zoom in a little bit, that this is a surface that we're standing on. Let's imagine that we're standing right here, right? If I move in the x direction, so I'm gonna imagine moving in the positive x direction. So right now the positive x is in this red, the red axis moving to the left of the screen. I imagine standing on this hill, moving in that direction, you would head down the hill, right? That's the interpretation. The derivative would tell you what happens to the value of this surface, in this case, the height of this hill I'm imagining standing on. If I move in the positive x direction, I would lose height. If I moved in the positive y direction, that's going to be down the hill this way. I'm going to lose height as well. but it looks like it's going to be a whole bunch steeper. Let's examine this in from another direction. Let's turn this around, because now I've got this aligned a little bit differently. So let's imagine standing on this point right here. Now if I move in the positive x direction, I'm moving up the hill, so the derivative with respect to x would be positive. But if I move in the positive y direction, that's going to be back into our screen. I'm moving down the hill over there, right? You can see it sort of sloping downward that way, right? So this is, I think, the easiest way to understand this, right? You're standing on a hill. Depending on the direction you move, you may move up at a fast rate, up at a slow rate, down at a fast rate, down at a slow rate. If sometimes you move and you stay at the same height, right? Those contour lines we talked about last time are directions where you're staying at the same height, and that could happen where moving in the x or y direction doesn't change the height you're at. So all of these things can happen, okay? And so that's why we have to look at, right? It's hard to talk about the rate of change of this function z, right? How does it change as you change the input? Because now our input doesn't have an obvious direction to check, right? When we had one-dimensional, when we had one single variable functions, we just thought about increasing the input, but now we have two inputs, so we can think about each one separately, increasing y, increasing x, all right? All right, let's take this idea just a little bit further with a different example. Here is the function, this is z equals 5 minus x squared. Actually, let's just do it a little easier. 5 minus x squared minus 2y squared. Okay, that's what we're looking at a graph of here. Let's look at the point. Oh, sorry, I'm going to change one more bit of notation just because we haven't quite introduced some other notation yet. We'll do that right after this. Let's look at the point 1, 1. If that's the point. Okay. So at 1, 1, let's compute some partial derivatives. Let's compute the partial derivative with respect to x. We get 5 is a constant, that goes away. I get negative 2x minus 2y squared. This is all a constant. I'm thinking of y as my constant. At the point 1, 1, I get negative 2. In other words, what this is saying is at this point, a change in x elicits a unit change in x elicits a negative 2 unit change in z, in our function, right? Now, this is what the same understanding of derivatives have in single variable calculus, that we know that the shape of a function can change. And so if I say the derivative right here is like 3, what I mean is if I drew a tangent line here, it has a slope of 3, but the actual function might start changing in a different way immediately after leaving that point. So if you actually change the input by 1, you might not change by the derivative because the function continues to change, but we're saying at that point, a unit change in our function elicits that change, the derivative in the output. But we mean the same thing here. So let's look at something. This is at the point 1, 1. Let's look at the plane. I'm going to add to this drawing the plane y equals 1. Okay, so that's the plane we're looking at now. And the point 1, 1, let's see, let's just actually add it to this picture. The point 1, 1, you can put 1 into that equation, you'll see that the output is z equals 2. So we've got this point 1, 1, 2. That's the point we're looking at. And so right now we're staring down the y-axis. This blue sheet here is the plane y equals 1, and the shape we see is the intersection of our curve. It looks very much like a parabola at the place where y equals 1. That's the shape of it. A change in x, right? A positive change in x should make our output change by -2. Now notice, because of the way we're looking down the x-axis, a positive change in x is moving to the right. So what you can imagine is something akin to a tangent line, right? If I shift a little bit in the positive direction of x, if I move this way, right, I expect my function to decrease by -2, except immediately after leaving that point, the rate of change changes. Just like a tangent line in single variable calculus doesn't really tell us what happens anywhere else. It tells us what it looks like is happening right there. In other words, in this plane, I can think of x as a function, or sorry, z as a function of x by itself. I've fixed y to be 1 in this plane. Everywhere in this plane, y is equal to 1. And so we have this equation. Let's make it z equals 5 minus x squared minus 2, right? Because I'm putting in 1 for y. In other words, z is 3 minus x squared, which you can very clearly see this is the parabola of. Remember, our x values are switched. We'll flip it around in a minute, but we want to see this clearly for right now. We know that the derivative, we just computed it, is -2x. At this point, I could compute the tangent line. If I was only living in this plane where z is my output variable, I would have z minus 2, right? This is the point. Remember, I'm ignoring the y value right now. I'm thinking of this as just all living in this plane where we only have x and z. Our x input is 1, our z output is 2. So we do our tangent line formula. Z minus 2 is equal to the slope x minus 1. Or z equals -2x. We'll get plus 4. Okay. Let's graph that line. I've got it there. So let me erase my mess that's over there. Now again, we're looking at this thing backwards. So this looks like it's a positive slope, but it's only because we're looking at down the y-axis where our x values are to the positive x values are to the left. But notice this is a line with a y-intercept of 4, or in this case a z-intercept, and we can see that that's the case right there. Right, there's our intercept. Notice if I put in x equals 2, I get out 0. That's our x-intercept right there. So this is a graph of that tangent line if we were only dealing with this single plane. If we were in this plane, that's the tangent line that we would have. Okay, so let's flip this around for a second. All right, so now it's in the more traditional view. It's hidden behind the surface, but you can see that positive x is to the right now, and you can vaguely see that parabola in that plane. Okay. We can do the same thing in the y direction. If I fix a plane where x equals 1, I can come up with the same kind of idea for the tangent line in that direction. So now, right, this is the one in the plane y equals 1. Here's a tangent line in the plane x equals 1, right? So those two lines are saying if you traveled in the x direction, for instance, at this point on the surface, it's like you're traveling along this line. And if you traveled in the y direction at this point in the surface, you're traveling in the same way you would travel along this line. Of course, our surface changes as soon as we leave that point, right? It's bending away from those lines. But they give us these two notions of how we're traveling at that point. Later, we'll define something. I'll just give us a little preview. Something called the tangent plane, and it's going to be a plane that contains both of those lines, right? And it just kisses our surface right there in the same way that a tangent line just barely touches our functions at those points where they're built. Okay. Okay. So more to talk about with these. Oh, one more idea before we go. Sorry. Let's finish up by just adding a little notation to this. There are several other notations. So let's get rid of all this. So we've got, there we go, a list of notations, so I don't forget any. There's probably more, but these are some of the most common ones. So we use the notation, the partial with respect to x, like this. Sometimes we just write this. We will use this one a lot. df partial, partial f partial x. It's like a d, but it's a little more curly, I guess is one way to say it. We have the same thing, right? This is just like how when we write d dx times a function f of x, it's sort of like saying, this is saying take the action of a derivative on this function. Sometimes we write it with a z, because as we sometimes write z equals f of xy. So we'll write with z and x. And sometimes we just use numbers, especially if you're doing more than, that's an alert about the curfew coming in from the city. If you're hearing that beep, I hope it stops. If you're doing more than 2 variables, right? Sometimes we stop naming our variables, things like x, y, and z, and you just might say you have an x1 variable, x2 variable, x3 variable, because you have 10 variables. It's easier just to name them all the same letter. So you can use 1 to mean the derivative with respect to the first variable. Sometimes people use a d for the derivative, d of the first variable, or like we were doing earlier, this can be d x f, right? And then we get all the comparable versions in the y direction, right? So all these things. So again, what this is telling us is 2 things in each case. One, that we're taking partial derivatives, right? So this little curly d lets us know it's a partial derivative, and which variable we're taking it with respect to, right? Because we need to know both of those things. Okay, that's really it for this. I know the notation looks crazy. We will mostly use, let's say, I tend to stick with this one, this sort of first half of these, I guess. They'll become pretty familiar pretty quickly. We'll be doing a lot with these in the next few videos. Okay, that's it, everybody. Thanks a lot. I will see you next time.